Hey, everybody. The first thing I thought we would do is go over the exam. I'm just going to go over it briefly. I might work out a couple of problems if I feel that they're sort of, involved. So let me go ahead and share the screen. Okay. So question one, this is a round trip. Right away, the displacement is zero, right? The displacement vector points from where you start to where you end, and you're ending up at the same part that you started. The displacement is zero. The average velocity, therefore, is zero. The average velocity is the displacement vector divided by the time. Okay, so we have a strange planet, an object being launched at an angle, and you have the angle of inclination and the initial speed, and it gives you the time and asks you how fast is it traveling. Okay, so I will do this one after I get done showing you the exam. Yeah, after I get done showing the exam, relatively simple problem. Head to tail method, all you had to do was just switch the directions of B and C and link them head to tail, and you should have got toward the upper left. I throw a ball directly upwards. At the very top of the climb, its speed drops to zero. At that point in time, its acceleration will also drop to zero. Plainly false. I have told you in many times on in our discussions that the acceleration of the object is always 10 meters per second squared, all the way up, all the way down, and even at the top, if it's in free fall. Calculate the magnitude of the normal force on a certain brick. The brick is resting on the floor of an elevator, accelerating upwards at 3.41 meters per second squared. I did this problem also in lecture, and relatively straightforward. I don't think I need to do this one. You may disagree, but again, I did this problem pretty much verbatim in your lecture. An AR-15 rifle has a 0.5 meter long barrel. When fired, a bullet with a mass of 3.33 grams accelerates from rest and exits the barrel. It gives you the net force, and right away, you got the net force acting on a bullet of known mass, the acceleration. You've got to get the acceleration. You take the net force divided by the mass, and now you have the acceleration. And with the acceleration, you finish the problem by doing what? Applying the equations of motion. This one might take a little bit of time, but its solution is very straightforward. And it's a homework problem. Two forces, this problem taken directly from WebAssign, and really involved nothing more than vector addition. And as I mentioned, in preparation for the exam, you needed to know how to add two vectors. A marble moving with a uniform acceleration has a velocity of such and such toward the positive x direction, when its x coordinate is such and such. If its x coordinate at some time later is this value, what was the acceleration? This one here, you really needed to draw it out, and you have to understand what the displacement vector is. It points from the start to the final point. If you caught that, this is an easy problem. This is one maybe I can do on the board. A mortar shell is launched off the edge of a cliff at an angle of such and such. This is the same problem as the first one, well, not the first one, but the one above, but I'm asking you for the straight line distance. So instead of finding the velocity vector, you're finding the displacement vector. Other than that, it's the same. I fire a rifle bullet horizontally. How could I tell how long it takes for the bullet to hit the ground? I stated this explicitly in one of the recorded sessions, that if you drop a bullet at the same time you fire it, you can listen to how long it takes for the bullet you drop to hit the ground, and it's the same time for the bullet that you fire to hit the ground. This should have been just like that, because if you watch the videos, you should have picked up on this thing immediately. And there it is. So let me go back. I want to do, let's see, this problem here for you. And I need to draw that on the board, so hang on. Positive 8.20. When its x coordinate is 4.102. Okay, so at this point, its x coordinate is 4.102. .203 seconds later, it's at negative 1.6067. So here's 0. This is negative 1.67 centimeters. Centimeters per second. Centimeters. What was the acceleration? Okay, so the question now becomes, well, let's see here. We have to find, let's see. Let's find the displacement vector. Okay, what is the displacement vector? It points from its starting position here to this position here. What is this distance? It's going to be 4.102 plus 1.67. .102 plus 1.67. And notice it's negative because it points in the negative direction. Now we can apply our equations of motion. V is V naught T plus 1/2 AT squared. It's one of them. And V is V naught plus AT. Well, we have, let's do this one. The displacement vector. Well, let's see here. Let's just get rid of the 2 here, because all I care about is that you don't have to generally do it. So this becomes negative 5.77. So this is negative 5.77 is V naught positive 8.20 times the time, which is, I didn't write that down, 1.28. Okay, I forgot that you can't see the screen. Okay, so I'm going to stop the share and I'm going to start the problem over again, but at least I got it drawn up there. Okay, sorry about that. I just realized, and I've done this a number of times. I've gone through a problem that students have to stop me and say, we can't see what you're doing. Okay, but here's the problem. It said that V naught, initially V naught was at this point, positive 4.12 centimeters, and was moving at 8.2 centimeters per second in the positive direction. And then sometime later, in fact, it was 2t equal to 1.238, I think, it's here. And so the question now becomes, what's the acceleration? All right. Well, let's see here. D is V naught T plus 1/2 AT squared. Shouldn't have to look this up. You should know it. The displacement is 5.77 negative. V naught is 8.20 times the time plus 1/2 A. I'm going to leave the vector on top and not assume I know the direction, although I can tell you right now it's got to be in that direction. If the object was accelerating in this direction with this velocity, it has to go faster and faster and faster in that direction. We'll never go in that direction. Okay. times t squared. Okay, from this, we can solve for A. It's one equation, one unknown. I'll let you do it. I don't want to go through all this. But at any rate, multiplying through by 2, you get rid of that 1/2, and then divide it by 1.238 squared, and you should be able to get the acceleration. Now, if you want to know what the final velocity is, you just go to this equation. The initial velocity is 8.20 positive, plus the acceleration that you just found, which is going to be negative, by the way, times the time. And now you can solve for the final velocity. Two-step problem if you're looking for the final velocity. I can't remember what it was asking for, but at any rate, that's how this problem is done. Now, for the two projectile motion problems, just go over my lecture notes. I showed you how to do that problem explicitly, okay? So if you still have questions on it, come to my office hours, but at any rate, I got to kind of move on here. The key to this problem, by the way, is making sure that you drew it and being careful with your signs. Which directions do these arrows point? You make a mistake there and you will miss it. Okay, the next thing we're going to look at is the infamous two-body problem. When I say infamous, it's no harder than the others. Okay, so I'm going to give you a typical two-body problem. All right, and it looks like this. You have a table, and we have a pulley here. The pulley is massless and frictionless, so it spins easily. We have a mass here, we'll call it M1, and it's attached to a hanging mass, we'll call M2. And let's see, let me go ahead and give you some values here. M1, we'll say is 5 kilograms. This is the mass in kilograms. And we'll say that this one here is 2 kilograms. And let's suppose that this distance here is 3 meters. Now, this is frictionless. This is frictionless. There's no friction anywhere in the system. Okay. We're going to cover friction next. So don't worry about, being, deprived of anything. And the question is, how long does it take for this object here to hit the ground? And I know what you're thinking. This is impossible. What kind of crazy maniac physics professor gives us a problem that's impossible to solve? There's no way. You can bring in the smartest engineers and they'll never be able to figure this thing out, right? Well, again, what is the key? When faced with this insurmountable problem, you've never seen it before, what do you have to find? Well, the acceleration. Remember, it's going to be about solving this dealio here. And we need to find the acceleration somehow. What the acceleration of what? Our bodies. Now notice something. Whatever this one accelerates at, this one has to accelerate at too, because they're connected by a string. The string isn't allowed to stretch or shrivel up. Therefore, whatever motion this body has, this one has the exact same motion. Okay. So we need to find the acceleration of the system. And there's two ways of doing that. There's Newton's second law, and there's equations of motion. One of these two is going to have to provide the acceleration somehow. Now, this is constant linear acceleration because we haven't introduced any other kind of acceleration at this point. And therefore, I already know the equations of motion. It's d is v naught t plus 1/2 at squared, and v final is v initial is at. And of course, I know Newton's second law. It says if I vector sum all the forces acting on a system, I get the mass of that system times the acceleration of that system. And we notice there's A here, there's A here, there's A here. We gotta find A. Now, first thing I'm going to look at is the motion. It is easier to tell whether the equations of motion will find the acceleration than Newton's second law. And I take a look at this and I think, okay, wait a minute. No, by the way, I forgot to mention, we'll start this thing off at v equals 0. So in other words, I'm going to just let go of the system and let it go. Okay. So I know the initial velocity of my mass here, and I know that it travels 3 meters, but that's all I know. I don't know how fast it is traveling when it hits the ground. I don't know anything else. Therefore, if you look at the equations, you can tell the equations of motion are not going to do it. They are not going to provide the acceleration I need. Therefore, this problem is going to go in this direction. I'm going to apply Newton's second law and then find the acceleration. And then once I have the acceleration, I can substitute and find the time. Now, if I'm going to apply Newton's second law, I've got to remember, Newton's second law says the vector sum of all forces that act on a system is equal to the mass of that system times the acceleration of that system. The question now is, well, what's the system? Well, you can make it this object, you can make it this one, or you can make it both. And actually, if you make it both, you can solve this problem real easily. However, it's also not very robust. I can trip up that kind of deal pretty easily. I tend to like to choose one of the masses, apply Newton's second law, and see if I can get the acceleration. Okay, so let's do it. What are the forces that act on this is the system here. What are the forces that act on it? Well, we have gravity pulling down. This is 2 mass times g, which is 10, means this is 20 newtons. Remember, the force of gravity is mg. And this green is kind of going by the wayside here. I'm going to have to use it, I think. Okay, so we have this force of gravity. We also have the string pulling up. And we'll call this a tension force. That's what strings apply. We don't know how big it is. It is not 20 newtons. Do not assume the value of the tension force. It comes out of Newton's second law. So now we apply our Newton's second law. We get what? Well, we have the sum of the forces acting on the system. We have F of t going up, it's positive. Mg going down, that's negative. And that's equal to the mass of the system. This is the system, not this one. We're not combined, it's just this one. So this is 2 times the acceleration. Now, one thing I know is the acceleration points down, doesn't it? Right? When I let go, I know it's going to accelerate downwards. So I can go ahead and stick in here -a and take the arrow off. Those who put +a in here will not get the right answer. So now I can kind of clean this thing up here. I get F of t is equal to -2a plus 20. But unfortunately, I don't get the acceleration because I don't know what the tension force is. If I put a 20 in here, by the way, I would get A equals 0, which means that the object, that this thing is not accelerating, but it does accelerate. So don't do that. So now what I'm going to do is turn my attention to this one. And I'm going to do the same thing. To apply Newton's second law, I need to find the forces acting on the system. Well, let's see here. There's a string pulling to the right, F of t. By the way, these tension forces are the same value if this pulley is massless, and it is. You'll learn a little bit later that when this is not massless, they can't be the same value, but okay. And we also have gravity acting down, that's 50, and the force of normal force going up, holding it up, that's the force applied by the table. And we look at this and we think, wait, I have vectors of 2 different directions here, but this is a vector equation, which means it applies in any direction I want. Therefore, I can write Newton's second law as the vector sum of all forces acting in the x direction is equal to the mass times the acceleration in the x direction. This is the x direction. This is the y direction. And I can also write it as the vector sum of all forces in the y direction is equal to the mass times the acceleration in the y direction. Well, let's do this one first. Now notice, my vectors are all good vectors here. I don't have any vectors pointing off at weird angles. If I did, I'd have to break that vector into those components. And that's one of the variations of this problem that will show up in your homework. All right, so I'm going to vector sum the forces in the x direction, but there's only one, F of t. So I get positive F of t. That's in the positive direction. And it's the only one, so it is the vector sum, is equal to the mass of the system, which is 5, times the acceleration of the system, A. The acceleration points to the right, positive. And this A and this A are the same A, because I remember I told you that whatever this one accelerates at, this one also has to accelerate. Well, now I noticed that, well, F of t is equal to 5a. I can substitute, I don't plug, I substitute my 5a into here. Now when I bring this over here, I would get 7a equal to 20. A is 20 divided by 7, which is pretty close to 3. 2 point something, 2.9 or something like that. Okay. Therefore, I applied Newton's second law. I had to choose 2 different systems to do it, but I applied Newton's second law. I found the acceleration. How do I finalize the problem? By applying the equations of motion. So now I look at this and think, well, let's see here. This equation here would look pretty good, I think, because I have a displacement. So now I go ahead to this equation. And I say, what is the displacement? 3 negative. Object is descending. So I get -3 is equal to the initial velocity, well, that's 0 times t, plus 1/2 times the acceleration. Its magnitude is 3, but it points down. Times t squared. Now I notice something. I can take the 0 out. The 3's cancels, the -3's cancels, and I get t is the square root of 2, 1.4 seconds. There it is. This thing here takes you from the start of the problem to the end of the problem. And it's systematic. Again, it's so important that you don't panic. All right. Now, if I had combined both of these masses together, I could apply Newton's second law. The only external force would be gravity acting on this one. The mass of the system would be now 7. You can get this answer out really quickly. I just don't recommend doing that. And when you start bringing in massive pulleys, it gets a lot harder to do that kind of thing. Okay, the two-body problem. Now, what kind of variations can come around on this? Well, oh, by the way, I didn't mention, I had vector sum of the forces on the y equal to mass times acceleration. I never actually did vector sum of the forces on the y. It turns out I didn't need it. When I vector sum of the forces on the x, I ended up getting the acceleration. Well, I got the ft equal 5a, I can substitute and get the acceleration. Okay, so in this case, we didn't need a vector sum of the forces in the y direction. When you have frictionless systems, that often happens. When you have friction, that rarely happens. Now, what kind of variation? Well, the most obvious variation is to make the table look like this. All right, in this case here, the force of gravity acts straight down. The tension force still acts like this. Okay, and then of course you have your normal force. What's different? Well, in this case, I told you this object is going to accelerate up the ramp. You want to slope your axis along the acceleration. And therefore, this is going to be positive x. This will be positive y. And you have a bad vector. The mg has to be broken into components. Not hard if you understand that this angle here, which will be given to you in the problem statement, is the same as this angle. And therefore, the component along this direction is mg cosine theta, right? Cosine touches. And therefore, this one is mg sine theta. Now that you have these two broken into components, you can take this one out and you can solve this problem just like we did with the other. Okay, that's the only complicating factor is when you slope on their axis here, now you have the gravity having a component along the x and along the y, and you have to do something about it. Okay. Other than that, not much harder. What about friction? Friction does kind of introduce some complications. Okay, so what I have here is a big box. It's fairly heavy, actually. And I'm going to attach a spring scale to it. Okay, and right now, actually, this should be reading 0. I'm not applying any force, and my box is not accelerating. Okay. I notice something. I pull with 2 newtons of force, This is a Newton scale. So I pull with 2 newtons of force, but my box doesn't accelerate. Wait a minute. If the 2 newtons of force I'm pulling is the only horizontal force, then the vector sum of all forces would be 2. What must also be showing up? Think about that. There must be a force in the opposite direction that offsets the 2. Vector sums, when I take my 2 newtons in this direction and that one in the other direction, those 2 must vector sum to 0. It must be 2 newtons as well. Now I'm going to pull a little bit more, and I pull with 3 newtons, and the box still doesn't accelerate. So now the force in the opposite direction, which you're probably guessing right now is friction, is 3 newtons. Then I pull with 4. The force of friction must increase to 4 newtons. And if I pull with more and more force, the force of friction is going to rise in what they say at the same time, concomitantly with this 4. So as I increase more and more, the force of friction rises more and more to always keep this box from accelerating. Then all of a sudden, though, the box begins to accelerate. It was initially at 0 velocity. It's now not 0. It must have accelerated. So in sum, the force of friction that is keeping this box from moving is going to rise to match whatever is trying to accelerate the box to a certain point, in which case it can't add any, it can't do any more. Let's do this one more time. See what this maximum force is. Okay, so I pull 4, 6, oh, about 6, isn't it? I get about 6, it starts to accelerate. Okay, so now this is called the static case. The static case. This is the static case. And that means that this object here is not sliding over this surface. That's static. If it's sliding, it's called kinetic. Don't forget that. Okay, so in the static case, the force of friction applied by the surface on this box, because that's what's applying it, it's this surface here, on this box rises to the occasion to a certain maximum, and then it can't rise anymore. Then, once you exceed that, any extra force you apply is unmatched and the object accelerates. So we'll do 6 here. So initially, there was no force pulling, the force of friction was 0. Then I applied with 2 newtons, and the force of friction responded with 2 newtons. By the way, this is an example of an applied force. Okay. Then I applied with 4 newtons, and the force of friction. And by the way, I'm going to draw these force of frictions at the surface because the surface is providing it. So the surface is providing 4 newtons of friction. Then I get to 6 newtons. And my force of friction responds with 6 newtons, but this is the maximum amount that it can. Now, what happens if I apply 7 newtons? If I apply 7 newtons, the force of friction is 6 newtons. It's reached its maximum. I end up, therefore, with a 1 Newton vector sum. So, and let's just give this a mass of, let's say, 2 kilograms. Now when I vector sum the forces in the x direction, equal to the mass times the x direction, times acceleration in the x direction, I get -7 plus +6 is equal to the mass times the acceleration. This is -1. My acceleration comes out to -0.5, which means it accelerates in this direction by 0.5. Okay. So first lesson learned about friction. The force of friction takes on values up to a maximum value in the static case. Now, once the object starts to slide, that's no longer the case. The force of friction is a certain amount. But in the static case, it will rise up to some maximum value. Now, the next question is, well, what determines how much friction what determines this maximum amount that it can apply? Well, let's look at that. Now, this part of the class is not much fun online. In class, I have a lot more fun going over this. But boo-hoo-hoo-hoo. All right, so we have here our object, certain mass. And I apply a force here. And I'm going to get a certain force back. And the question is, what determines how big this thing is? And by that, I mean, what determines the maximum value that this thing can take on? Well, I'll go ahead and just tell you. The force of friction, the maximum value that this can take on in the static case, this is static. This is not accelerating across your view. I'm going to make this one here small. This has to be the same length. Is given by the coefficient of static friction times the normal force. The normal force, what? The normal force provided by the surface that's creating the friction in the first place. I think, well, what the hell is this? It's a number. It's the coefficient, I'll just say it, coefficient of static friction. And it is a number. It does not have to be less than 1. It can go up to like 3. I don't think I've seen anything above 3, but it doesn't have to be below 1. But you can think of this as the sticky factor. Or the roughness factor. I better write this out. This is the coefficient of static friction. But the rougher the surfaces are with respect to each other, the higher the coefficient. And by the way, this is between two surfaces. You cannot say that the coefficient of static friction of glass is 0.5. You have to ask, what's the other material? And so the coefficient of wood rubbing on glass might be 0.5, but like sandpaper on glass might be like 0.6. So you always have to have two surfaces combined. It's the coefficient of static friction between these two surfaces. Okay. And of course, this is going to be the maximum value, but the coefficient of friction, the friction amount can be any number below this. Okay, just remember that. The reason why I say that is because I often give problems where this is a 2 Newton force, and when they do all this, they get 3 newtons when they calculate this, they get 3 newtons. We'll tell you what, let's just do it. I'll show you where students make mistakes. Well, here is a typical example. Oh, I've nailed a bunch of students on this one. So I have my mass. Let's say it's 2 kilograms. That means what? The force of gravity down is 20 newtons, and the normal force points up, and I'm going to pull on this object with a force of 5 newtons. Now I'm going to define a coefficient of static friction of 0.5. And I ask students all the time, what happens to the box? And they say, oh, okay, I know this equation. Force of friction, static case, is equal to mu sub k, mu sub s, times the normal force. Now I got to find the normal force, but here that's not too hard. I vector sum the forces in the y direction. I get F of n acting up, 20 acting down. This object is not hopping, it's not accelerating at all in the y direction. And so I get the normal force is equal to 20. And so they come over here and say, oh, okay, now I know the force of friction, static case, is the coefficient, 0.5, times it by the normal force, which is 20, and they get 10 newtons. So what they do is they say, oh, this is 10 newtons. Then they vector sum the forces in the y in the x direction. And again, well, see, we've got 10, 5, and that's equal to the mass times the acceleration. So they get A equal to 2.5. What? What does this say? If I pull on it this direction, it's going to accelerate to the right in that direction. So pulling on my mass makes it accelerate in that direction? No. Their mistake was they assumed that this 10 newtons was the force. This is the maximum amount. It's not going to go to 10. It only needs 5. So this is actually just going to be 5 newtons. And the acceleration is 0. In other words, this force here is not enough to break the object loose from the surface. Don't get caught on that. Remember, this only tells you the maximum amount. The actual force of friction provided on an object in the static case is anywhere up to this value. It could be 0. Okay. Now the question becomes, well, what happens when the object breaks loose? Now when it breaks loose, you have the kinetic case. So we'll leave this equation up here. What happens if we do provide enough force to overcome friction? Now we get the object sliding, what happens? In this case, we use the same equation. Now we're talking about the kinetic case. And there's a couple of changes. One, this is not the maximum amount. This is the amount. Okay? The other one is the coefficient changes. It gets smaller. if you've ever had to try to push a refrigerator and you're like, as soon as you get it to move a little, it starts to become easier to move. And the reason why is because the coefficient of friction drops, because the coefficient of the kinetic case is lower than the static. Okay, so once I apply a larger force, all right, so let's just say that U sub S is 0.5, U sub K is 0.25. It's got to be less than in the static case. And we have a 2 kilogram here. Now what happens? Okay, well, first of all, I have to ask myself a question. By the way, this will be on your exam at some point, either next exam or the finals. Pay attention to this. I have 2 kilogram body. I have 20 newtons I'm pulling on it. This is my applied force. I have a static coefficient of 0.5 and a kinetic coefficient of 0.25. Okay, the question is, what happens to the box? The first thing you have to ask is, does it accelerate at all? Well, to find out if it accelerates at all, you apply the static case. You use this to find out what is the maximum amount of friction that this surface can provide, and then see if this overcomes it. All right, so we have 20 newtons down, normal force going up. This is the force of gravity, of course. When we vector sum the forces in the vertical, we get Fn minus 20 equals 0, no acceleration in the vertical. The normal force is 20 newtons. This tells me how much friction is available, maximum available. And so the force of friction in the static case is the amount, which is 0.5, I'm sorry, the coefficient of static friction, 0.5 times the normal force, 20, and that comes out to 10 newtons. Therefore, my 20 will overcome the 10. And that's all I know so far. This crate will accelerate. And as soon as it starts to move, it changes the coefficient from the 0.5 to the 0.25. Don't forget that, because I'll ask you for the acceleration amount, and students often use the same coefficient. This 10 newtons here was calculated in the static case. Once this object starts to move, the force of friction is no longer 10. What is it? Well, we go to this equation. The force of friction in the kinetic case is 0.25 times the normal force, 20, which is 5 newtons. Now, when we go to vector sum our forces, we have 5 newtons going in the opposite direction, force of friction. So now we sum the forces in the x direction equal to the mass times the acceleration in the x direction. We have positive 5 minus 20 is equal to the mass times the acceleration. And we get negative 15 divided by 2 is A, which is negative 7.5 meters per second squared. Negative means what? It's going to accelerate in the negative direction. This is exactly kind of what we figured. Okay, so make sure you understand the static one, this is only a maximum value. They often write it this way. Instead, they just take the maximum off and they say it's less than or equal to. It's the same statement. Okay? And you have to first find out in a static case if the force of friction is going to be high enough to keep this object from accelerating. If it's not, you got to do the problem all over again from the start using a different, the kinetic coefficient. I think I said that right. Yeah, I think so. Okay. Anyway, there it is. That's how friction works. And the next time we get together, we'll start doing some real serious problems with friction.